Take a deep breath and look at your hand. Really look at it. The calcium in your bones, the iron in your blood, the oxygen you just inhaled. Where did these come from? Not from Earth. Not from our sun. They came from stars that died before our world was even born. Every single atom that makes you who you are was forged in the nuclear heart of an ancient star billions of years ago. You are not just in the universe. You are made of the universe. You are stardust that learned to think, to feel, to wonder. And tonight, we will follow your atoms on their impossible journey from the core of dying stars to this very moment. Are you ready to discover the most beautiful truth about your existence? Let us travel back beyond memory, beyond time itself. 13.8 billion years ago, the universe explodes into existence in a brilliant flash we call the Big Bang. But this newborn cosmos is nothing like the rich, complex universe you know today. There are no stars yet, no planets, no life. In these first moments, the universe is a seething ocean of pure energy, so hot and dense that matter as we know it cannot even exist. Particles are created and destroyed in fractions of a second. Everything is light and heat and violent potential. This is where your story begins, in an inferno of pure possibility. As the universe expands, it cools. And as it cools, something miraculous happens. Energy begins to condense into matter. First, the tiniest building blocks appear. Quarks bond together to form protons and neutrons. Electrons swirl into existence. And then, about 3 minutes after the beginning, these particles start to stick together. The first atomic nuclei are born. But here is the remarkable thing. The universe can only create the two simplest elements, hydrogen with just one proton and helium with 2 protons and 2 neutrons. That is all. The entire early universe is made of nothing but hydrogen and helium. For hundreds of millions of years, the universe remains in darkness, a formless void filled with invisible clouds of hydrogen and helium drifting through the expanding emptiness. This period is called the Cosmic Dark Ages, and it is a universe almost unimaginably different from our own. There is no carbon to build life, no oxygen to breathe, no iron, no silicon, no calcium. None of the elements that will one day make planets or trees or your beating heart. All the complexity of matter, all the richness of chemistry that makes existence interesting, does not yet exist. But the seeds of change are being planted. Gravity, patient and relentless, begins its work. These vast clouds of hydrogen and helium start to collapse under their own weight. Slowly at first, then faster. Gas falls inward, drawn by invisible forces. As it falls, it heats up. Atoms collide more and more violently. Temperatures rise. Pressure builds. Pressure builds. In scattered pockets across the dark universe, something is stirring. The clouds are forming knots, dense cores where the gas is becoming unimaginably hot. These cores are like cosmic eggs, incubating the future. And after hundreds of millions of years in darkness, the universe is about to ignite. And then it happens. Deep in the heart of one collapsing cloud, the temperature reaches 10 million degrees. At this threshold, hydrogen nuclei are moving so fast that when they collide, they do not bounce off each other. They fuse. They merge into helium, releasing tremendous energy in the process. This is nuclear fusion, the fire that will power the stars. And in that instant, the first star ignites. A brilliant point of light pierces the cosmic darkness. The universe, for the first time in its existence, can see. The age of stars has begun, and with it, the age of creation. These first stars are like nothing we have in our universe today. They are monsters, hundreds of times more massive than our sun, burning with such ferocity that they shine with the light of millions of modern stars. They live fast and die young, consuming their fuel in just a few million years. But their brief lives have a purpose. Inside their cores, where temperatures reach hundreds of millions of degrees, nuclear fusion is creating new elements. Helium atoms are being forged into carbon into oxygen. These first stellar giants are the universe's first alchemists, transforming simple hydrogen into the building blocks of complexity. But even these mighty stars cannot create the heavier elements. Not yet. They can make carbon and oxygen, even trace amounts of neon and magnesium. But to forge iron, to create gold and uranium and all the heavy elements that will become essential for life, the universe needs something more extreme. It needs violence. It needs death on an unimaginable scale. These first-generation stars, burning through their fuel at a reckless pace, are hurtling toward a cosmic catastrophe. And when they die, they will scatter their newly created elements into space, seeding the cosmos with the raw materials for everything that follows. Your story is about to take a dramatic turn. This is where we stand now, at the threshold of understanding. The universe has gone from having only 2 elements to having half a dozen. It has gone from total darkness to being lit by countless brilliant stars. But the journey toward the incredible complexity of a living, thinking being, requires one more ingredient. It requires the most violent events in the cosmos. It requires supernovae. And it requires the strange, beautiful alchemy that happens only in those final, explosive moments when a star tears itself apart. Let us witness this cosmic forge where your atoms were truly born. To understand where you came from, we must first understand the engine of creation itself. Every star, from the smallest red dwarf to the largest blue supergiant, is a fusion reactor. At its core, the temperature and pressure are so extreme that the normal rules of matter break down. Atomic nuclei, which would normally repel each other, are forced together with such violence that they merge. This is fusion, and it is the source of all the light you see when you look up at the night sky. But it is also the source of every element in your body. In the core of a star like our Sun, 4 hydrogen nuclei are forced together through a series of reactions to create one helium nucleus. This process releases energy, which is what makes the star shine. But something else happens too. The helium nucleus weighs slightly less than the 4 hydrogen nuclei that created it. That missing mass has been converted into pure energy, following the famous equation you know. Billions of years, this is all that happens. Hydrogen becomes helium. The star shines. It is a simple, elegant process that keeps stars stable for eons. But what happens when a star runs out of hydrogen in its core? For smaller stars like our Sun, this is nearly the end of the story. They will swell into red giants, fuse some helium into carbon and oxygen, then gently shed their outer layers and fade away as white dwarfs. But for more massive stars, running out of hydrogen fuel is just the beginning of a spectacular transformation. The core contracts. The temperature rises. And at 100 million degrees, a new kind of fusion ignites. Helium nuclei begin to fuse together, creating carbon. The star has found a new lease on life, but helium fusion produces far less energy than hydrogen fusion. The star burns through its helium in a fraction of the time it spent fusing hydrogen. For a massive star, The helium era might last only a few 100,000 years. When the helium runs out, what happens next? In truly massive stars, those at least 8 times the mass of our Sun, the temperature climbs even higher, 600 million degrees. Day, and a third fusion process begins. Carbon nuclei are slammed together to create neon and magnesium. The star refuses to die. It keeps inventing new ways to generate energy. Now, the process accelerates. Carbon fusion lasts only a few thousand years before that fuel is exhausted. The core contracts again, 1 billion degrees. Neon fuses into oxygen. That phase lasts perhaps a year. Then oxygen fuses into silicon. 6 months. The star is like a cosmic pressure cooker, each new fusion process requiring higher temperatures and producing less energy. The core is building up layers like an onion, each shell fusing different elements. Hydrogen on the outside, helium beneath that, carbon, neon, oxygen, silicon. The star is becoming a chemical factory, creating heavier and heavier elements in its desperate attempt to stay alive. Finally, silicon begins to fuse in the core. This is the last stand. Over the course of just a few days, silicon nuclei are forged into iron. And then the star reaches a fundamental barrier. Iron is special. It is the most stable element in the universe. Fusing iron nuclei together does not release energy. It requires energy. For the first time in the star's life, fusion in the core cannot generate the outward pressure needed to support the star's immense weight. The nuclear fire that has burned for millions of years suddenly goes out. The core, now made of pure iron, is about to face its final moment. This iron core is perhaps the size of Earth, but it weighs more than our Sun. It is the densest object the universe has ever created, short of a black hole. For a brief moment, it sits there in the heart of the star, inert and dead. The outer layers, still fusing lighter elements, press down with unimaginable force. And then, in less than a second, the core collapses. Not slowly, not gradually. In a heartbeat, it shrinks from the size of Earth to the size of a city. The atoms themselves are crushed. Electrons are forced into protons, creating neutrons. The rebound from this collapse sends a shock wave of unimaginable power racing outward through the star. That shock wave is the beginning of a supernova. As it races through the star's outer layers, it heats them to billions of degrees in an instant. And in that moment of unimaginable violence, something miraculous happens. For the first time in the universe's history, conditions exist to create elements heavier than iron. Gold, silver, platinum, uranium, every rare and precious metal, every heavy element that cannot be made in normal stellar fusion is created in this instant. The atoms that will become you are being forged in the heart of an exploding star, and in a few hours they will be scattered into space to begin their long journey. Imagine standing in the darkness of space, light years away from a massive star. For millions of years it has been a steady beacon in the cosmic night, and then, without warning, it begins to brighten. Hour by hour it grows more luminous. In just a few days, this single star becomes brighter than all the hundreds of billions of stars in its galaxy combined. For a few weeks, it shines with the power of 1 trillion suns. This is a supernova, the most violent and luminous explosion the universe can produce. It is death on an astronomical scale, but it is also the most important event in your personal history. The energy released in a supernova is almost beyond comprehension. In the span of a few seconds, the collapsing core releases more energy than our sun will produce in its entire 10 billion year lifetime. Most of this energy escapes as neutrinos, ghostly particles that barely interact with matter. But even the tiny fraction that remains is enough to blow the star apart. The outer layers, containing all the elements the star has spent millions of years creating, are hurled into space at speeds of tens of thousands of kilometers per second. The star is tearing itself to pieces. What is left behind is equally remarkable. At the center of the expanding debris cloud, there is often a neutron star, a ball of pure neutrons roughly 20 kilometers across but containing more mass than our sun. It is the densest stable object in the universe. A teaspoon of neutron star material would weigh as much as Mount Everest. Some neutron stars spin hundreds of times per second, their magnetic fields channeling radiation into tight beams that sweep across space like cosmic lighthouses. We call these pulsars. They are the beating hearts left behind by dead stars, but some supernovae leave behind something even stranger. If the original star was massive enough, more than about 20 times the mass of our sun, the core collapse does not stop at forming a neutron star. The gravity is so intense that nothing can halt the collapse. The core shrinks past the neutron star stage and continues to compress. It crosses an invisible boundary, a point of no return. A black hole is born. A region of space-time so warped by gravity that not even light can escape. Ultimate remnant. Cosmic punctuation mark at the end of a star's life story, but let us follow the material that was expelled. The expanding shell of gas and newly forged elements races outward at a significant fraction of the speed of light. It collides with the surrounding interstellar medium, the thin gas and dust that fills the space between stars. The impact creates a glowing shock front, a vast bubble of superhot plasma expanding through space. This bubble, called a supernova remnant, can be hundreds of light years across. And within it, your atoms are mixed with the ancient hydrogen and helium of the early universe, creating a rich cocktail of every element on the periodic table. Over tens of thousands of years, the supernova remnant continues to expand and cool. The shock front slows down as it sweeps up more and more interstellar material. Gradually, the violent explosion transforms into a gentle, glowing nebula. The elements forged in the heart of the dying star are now mixing thoroughly with the gas clouds of space. Carbon atoms from the stellar core drift alongside oxygen molecules. Iron nuclei mingle with wisps of hydrogen. The gold atom that might one day be part of a wedding ring floats next to calcium that will become bone. This mixing is essential. It ensures that the next generation of stars will have access to all the elements. Think about this for a moment. Every atom of carbon in your body, every molecule of oxygen you breathe, every trace of calcium in your bones, every bit of iron in your blood was created inside a star. Not our sun. Our sun is not massive enough to create these elements. They came from older stars, stars that lived and died before our solar system existed. And the only way those elements could escape from their stellar prisons was through the violence of a supernova. You exist because stars died. Your body is made from their ashes. Oh. This is not a metaphor. It is the literal, scientific truth, and supernovae do more than just create and distribute elements. The shock waves they produce compress nearby gas clouds, triggering the formation of new stars. In a very real sense, dying stars give birth to new ones. The cycle of stellar life and death is self-perpetuating. Each generation of stars enriches the interstellar medium with heavier elements so that the next generation is born from a richer chemical mix. The universe is gradually transforming from the simplicity of hydrogen and helium into ever greater complexity. And you are part of that progression. You are what the universe becomes after billions of years of stellar alchemy and evolution. Now we must zoom out and see the larger picture. Our Milky Way galaxy is a vast spiral containing hundreds of billions of stars. At any given moment, somewhere in this enormous stellar population, a massive star is dying in a supernova. On average, about 2 or 3 supernovae occur in our galaxy every century. That might not sound like many, but over the billions of years of galactic history, it adds up. Millions of stars have lived and died, each one contributing its newly forged elements to the interstellar medium. The galaxy is gradually becoming more and more chemically enriched. The elements expelled by supernovae do not stay neatly confined. They spread out, mixing with the vast clouds of gas and dust that occupy the space between stars. These interstellar clouds are huge, often hundreds of light years across, yet incredibly diffuse. In the densest regions, there might be only a few hundred atoms per cubic centimeter. That is a better vacuum than anything we can create on Earth. Yet these clouds contain unimaginable amounts of material. A single large molecular cloud can contain enough matter to form hundreds of thousands of stars. Within these clouds, the elements from countless dead stars are thoroughly mixed. A hydrogen atom from the Big Bang drifts alongside a carbon atom from a star that died 6 billion years ago. An oxygen molecule created in a supernova 3 billion years ago tumbles next to silicon atoms from an even more ancient stellar death. It is a cosmic soup, a treasure trove of raw materials waiting to be assembled into something new. But the clouds are cold, just a few degrees above absolute zero. They are patient, drifting through the galaxy's spiral arms, accumulating mass over millions of years. But nothing in the universe remains static forever. Eventually, something disturbs the tranquil cloud. Perhaps it is the shockwave from a nearby supernova. Perhaps it is the passage through one of the galaxy's spiral arms, where the density of stars and gas is higher. Perhaps it is the gravitational influence of a passing star cluster. Whatever the trigger, part of the cloud begins to collapse under its own gravity. As the gas falls inward, it fragments into smaller and smaller clumps. Each clump becomes denser, hotter. They are the seeds of new stars. And because they are collapsing from an enriched cloud, they contain not just hydrogen and helium, but all the heavier elements too. This is how the universe builds complexity. The first generation of stars was made only from hydrogen and helium. They created and distributed the first heavier elements through supernovae. The second generation of stars formed from clouds enriched with those elements. They lived, died, and added even more heavy elements to the mix. With each stellar generation, the interstellar medium becomes richer in the building blocks of complexity. By the time our solar system was ready to form, about 9 billion years into the universe's history, the local gas cloud had been enriched by countless previous generations of stars. It was ready to make something special. Let us talk about the distances and timescales involved here. A typical atom of carbon in your body was created inside a star that might have been thousands of light years away from where our sun now sits. After the supernova, that atom spent millions of years drifting through space, carried by stellar winds and shock fronts, gradually making its way to the molecular cloud that would become our solar system. It traveled across a substantial fraction of the galaxy. Your atoms are cosmic wanderers. They have journeyed farther and seen more of the universe than any human spacecraft ever will. This process is ongoing. Right now, at this very moment, Massive stars throughout the galaxy are in the final stages of their lives. Within the next hour, at least one star somewhere in the Milky Way will explode as a supernova. New elements are being forged and scattered into space. New molecular clouds are being enriched. New stellar nurseries are forming. The cycle that led to your existence is still turning, still creating the conditions for future complexity. Perhaps, in a molecular cloud forming today, there are atoms that will one day be part of a living being on a planet orbiting a star not yet born. The cosmic story continues. 4.6 billion years ago, in a quiet spiral arm of the Milky Way galaxy, there was a molecular cloud. It was not special. There were millions like it scattered throughout the galaxy. But this cloud, later generations would call it the solar nebula, contained something remarkable. After 9 billion years of stellar cycles, after countless supernovae had enriched the interstellar medium, this particular cloud had accumulated about 2% of its mass in elements heavier than helium. That might not sound like much, but it was enough. Enough carbon. Enough oxygen. Enough silicon, iron, and all the other elements that would be needed to build planets. And eventually, to build you, something disturbed this peaceful cloud. Perhaps a nearby star went supernova, its shockwave compressing a region of the nebula. Perhaps the cloud simply reached a critical density as it drifted through the galactic disk. Whatever the trigger, a portion of the cloud began to collapse. Gravity pulled material inward toward the center. As the cloud collapsed, it began to spin faster, just as a figure skater spins faster when they pull in their arms. The collapsing cloud flattened into a disk, with most of the mass falling toward the center. This disk was vast, stretching out hundreds of times farther than Earth's orbit around the sun. And it was about to give birth to a star system. At the center of this swirling disk, where most of the mass was concentrated, the temperature and pressure were rising. Material falling inward released gravitational energy as heat. The center grew hotter and brighter. This was the proto-sun, not yet a true star, but a glowing ball of gas held up only by the heat of its ongoing collapse. Around it, the disk of gas and dust rotated, each particle following its own orbital path around the growing central mass. It looked almost tranquil from a distance, this spiral of matter slowly being organized by gravity. But up close, it was a chaotic environment of colliding particles and ever-changing conditions. In the disk around the proto-sun, something remarkable was happening. In the coldest, densest regions, particles of dust were sticking together when they collided. These dust grains, each one smaller than the width of a human hair, were the solid condensation of those heavy elements forged in ancient supernovae. Silicon and oxygen formed tiny crystals of minerals. Iron condensed into microscopic metallic flakes. Carbon existed as both graphite and organic compounds. These grains collided gently, held together by weak electrostatic forces and the faint stickiness of ice. Grain by grain, they built up into larger aggregates. Pebbles, then rocks, then boulders. Over the course of perhaps 1 million years, these growing rocks reached kilometer sizes. Now they had enough gravity to actively pull in nearby material. They were no longer just passively accumulating whatever they happened to collide with. They were actively attracting matter. We call these objects planetesimals, the building blocks of planets. Tens of thousands of them orbited in the solar nebula, ranging in size from kilometers to hundreds of kilometers across. They collided frequently, sometimes gently merging, sometimes violently shattering. It was a cosmic game of billiards, with the largest planetesimals gradually sweeping up most of the available solid material in their orbital zones. Then, after about 10 million years of chaos and growth, the protosun reached a critical threshold. The temperature at its core climbed above 10 million degrees. Hydrogen fusion ignited. The sun became a true star, suddenly pouring out intense radiation and powerful stellar winds. This radiation blast swept through the inner solar system, blowing away most of the remaining gas and dust. The planet-building process suddenly had a deadline. The light, volatile materials were being stripped away. Only the solid, rocky material could remain in the inner solar system. This created a fundamental division that persists to this day. Rocky planets close to the sun, gas giants in the outer system where volatiles could survive. In the inner solar system, where the heat from the young sun was most intense, 4 large rocky bodies had emerged victorious from the planetesimal collisions: Mercury, Venus, Earth, and Mars. Each one had gathered up most of the solid material in its orbital zone. They were battered and scarred from millions of years of impacts, their surfaces molten from the energy of collision after collision. But they were intact. They were planets. And one of them, the third rock from the sun, had accumulated a special mix of elements and found itself at just the right distance from its star. Not too hot, not too cold. This planet had a future unlike any other in the solar system. It was Earth. Let us focus now on Earth, this ball of rock and metal that would become your home. 4.5 billion years ago, Earth had just finished its main accretion phase. It was a hellish world, nothing like the blue-green paradise we know today. The surface was an ocean of molten rock, heated by the constant bombardment of remaining planetesimals and by the decay of radioactive elements mixed into its bulk. There was no solid ground. No water. No atmosphere to speak of, just wisps of rock vapor boiling off the magma surface. This was Earth in its infancy, a world of pure chaos and heat. Yet within this chaos, organization was beginning to emerge. Something remarkable happened inside this molten world. The elements, mixed together in the planet-forming chaos, began to separate by density. Iron and nickel, the heaviest abundant elements, sank toward the center. Lighter silicates floated toward the surface. Over the course of perhaps 50 million years, Earth differentiated itself into distinct layers. An iron-rich core at the center, a thick rocky mantle surrounding it, and eventually, as the planet cooled, a thin solid crust forming on the surface. This differentiation was crucial. The metallic core would eventually generate a magnetic field to protect the planet. The rocky crust would provide a stable foundation for continents and life. But Earth's story took a dramatic turn about 50 million years after its formation. There was another planet-sized body in the inner solar system, likely formed at one of Earth's stable orbital points. This object, sometimes called Theia, was perhaps the size of Mars. For millions of years, Earth and Theia coexisted peacefully. Orbits change. Gravitational interactions with other planets slowly perturbed Theia's path. Then, one day, 4.4 billion years ago, a catastrophe struck. Theia collided with Earth in a glancing blow, the most violent impact in our planet's history. The collision vaporized a huge portion of both worlds. The debris from this collision, a massive cloud of molten rock and vapor, was thrown into orbit around what remained of Earth. Within hours, the cloud began to coalesce. Droplets of molten rock merged in orbit, rapidly forming a ring system around the battered planet. And then, over the course of perhaps just a few years to a few centuries, the ring material accumulated into a single large body orbiting Earth. This was the birth of the Moon, companion, our cosmic neighbor. It formed from the very substance of Earth itself, mixed with the remains of the impactor. The moon is literally a piece of our planet, thrown into the sky and shaped into a new world. This collision had profound consequences. It tilted Earth's axis, giving us seasons. It increased Earth's spin rate, making days shorter. The vaporization of the crust released vast quantities of gases that would later condense to form oceans and atmosphere. And the moon itself would play a crucial role in stabilizing Earth's tilt over geological time, making the planet's climate more stable and predictable. Without this collision, Earth would be a very different world, perhaps too unstable for complex life to evolve. In a strange way, this violent catastrophe may have been one of the luckiest events in Earth's history. The collision that almost destroyed our planet may have been what made it perfect for life. Over the next few 100 million years, Earth continued to cool. The surface temperature dropped below the boiling point of water. And then came one of the most important moments in planetary history. It began to rain. Water vapor, released from the interior by volcanic activity and delivered by countless comet impacts, condensed in the atmosphere and fell as rain. Not a gentle shower, a deluge that may have lasted millions of years. The oceans were born, filling the low-lying basins between the first continents. And dissolved in those oceans were the elements forged in long-dead stars, carbon, nitrogen, the Rus, sulfur, all the ingredients needed for chemistry, or complexity, for life. Let us pause here and consider what Earth had become by this point. It was a water world with vast oceans covering most of its surface. Volcanic islands and the first small continents poked above the waves. The atmosphere was thick with carbon dioxide and nitrogen, with almost no oxygen. Constant volcanic eruptions released more gases from the interior. Lightning storms raged across the skies. Tides, pulled by the nearby moon, were immense, reshaping coastlines daily. It was still a harsh, alien world. But it was no longer just a ball of lifeless rock. The stage was set. The elements were in place. Chemistry was about to become biology. In the warm oceans of the young Earth, atoms from countless dead stars swirled and mixed. Carbon atoms that had been forged in the hearts of red giant stars. Nitrogen created in the last moments of supernovae. Hydrogen that had existed since the Big Bang. These elements were no longer locked in the rigid structure of rock. They were dissolved in water, free to move and interact. And interact they did. Carbon's unique ability to form full bonds with other atoms made it the perfect backbone for building complex molecules. In the energy-rich environment of early Earth, with lightning, volcanic heat, and intense ultraviolet radiation, simple molecules began to link together into larger structures. Among the first complex molecules to form were amino acids, the building blocks of proteins. In the famous Miller-Urey experiment, scientists showed that passing electricity through a mixture of gases thought to resemble early Earth's atmosphere produces amino acids spontaneously. Nature likely discovered this chemistry billions of years earlier. Amino acids accumulated in Earth's oceans, perhaps concentrated in tidal pools or around hydrothermal vents on the ocean floor. These hot springs, heated by volcanic activity, created chemical gradients and provided energy for ever more complex reactions. The oceans were becoming a vast chemical laboratory, experimenting with trillions of different molecular combinations. But there is a vast gulf between a mixture of organic molecules and anything we would recognize as life. What is life? At its core, life requires three things. It needs a way to store information, a genetic code that can be passed on. It needs a metabolism, a way to harness energy and build structures. And it needs some kind of boundary, a membrane to separate the inside from the outside and create a distinct entity. somehow, in Earth's oceans, these three components came together. We do not know exactly how it happened. It is one of the great remaining mysteries. But we know that it did happen, probably multiple times, in multiple ways. By 3.8 billion years ago, perhaps earlier, the first true cells existed. They were unimaginably simple compared to even the most basic life today. But they had crossed the fundamental threshold. They could reproduce, making copies of themselves. They could metabolize, breaking down molecules to extract energy. They could evolve, gradually changing and adapting as random mutations in their genetic material were filtered by natural selection. Life had begun. And it began by using the elements created in stars, the carbon chains of organic molecules, the phosphorus in genetic material, the iron in early enzymes. You are not just made of stardust. Life itself is built from stellar elements. There is no other way to make biology. These early cells faced a world very different from ours. There was almost no oxygen in the atmosphere. They survived by fermenting organic molecules or by using chemical energy from their environment. But then, about 2.4 billion years ago, something revolutionary happened. Some cells evolved the ability to harness the energy of sunlight directly. They developed photosynthesis, using light energy to split water molecules and extract hydrogen, releasing oxygen as a waste product. At first, this oxygen was absorbed by dissolved iron and other minerals. But gradually, the oxygen began to accumulate in the atmosphere. The great oxidation event had begun. It was one of the most dramatic transformations in Earth's history. Oxygen was toxic to most life that existed at the time. The Great Oxidation Event was likely a mass extinction, killing off countless species that could not adapt. But for the survivors, oxygen opened up new possibilities. Oxygen-rich metabolism is far more efficient than fermentation. It allowed cells to extract much more energy from the same amount of food. Complex, large, energy-hungry organisms became possible for the first time. Multicellular life evolved. Plants and animals developed. The stage was set for the entire drama of complex life on Earth. And all of this was powered by elements created in stars, organized by chemistry, and animated by evolution. Fast forward through hundreds of millions of years of evolution, through the rise of the first animals in the oceans, through the colonization of land by plants and insects and eventually vertebrates, through mass extinctions and explosive diversifications, through the age of dinosaurs and their extinction, through the rise of mammals. Finally, just a few million years ago, to the evolution of primates with unusually large brains. Primates that would become human. Every step of this journey was powered by stellar elements. The calcium in the shells of ancient sea creatures, the iron in the blood of dinosaurs, the phosphorus in the DNA of every organism, all created in stars. Now let us make this deeply personal. Let us talk about you specifically. An average human body contains about 7 billion atoms. That is a 7 followed by 27 zeros. Almost incomprehensible. But every single one of those atoms has a history stretching back billions of years. About 65% of your body mass is oxygen. Most of that oxygen is part of water molecules, but oxygen is also crucial in organic molecules. That oxygen was created inside massive stars at temperatures of hundreds of millions of degrees. It was expelled in supernovae and drifted through space for millions of years before being incorporated into the solar nebula. Your breath contains atoms from dead stars. About 18% of your body is carbon. This element is the backbone of all organic chemistry, the foundation of life itself. Carbon is particularly special because it was created in the helium-burning phase of red giant stars in a process that requires an almost miraculous coincidence of energy levels. If the physics were even slightly different, carbon could not exist in meaningful quantities, and life as we know it would be impossible. The carbon in your body was created in the hearts of ancient giants, stars that swelled to enormous sizes, fused helium into carbon, and then shed their outer layers to distribute that carbon through space. You are built from the ashes of red giants. About 10% of your body is hydrogen. This is the most ancient element in your body, the only element that can truly claim to be primordial. Most of your hydrogen atoms were created in the first 3 minutes after the Big Bang. They are 13.8 billion years old, nearly as old as the universe itself. When you drink water, you are consuming matter from the birth of time. Those hydrogen atoms have been part of countless molecules throughout cosmic history. They may have been part of the solar nebula, part of comets, part of the early Earth's oceans. They have been recycled through countless organisms before becoming part of you. You carry the beginning of the universe inside you. About 3% of your body is nitrogen. This element is crucial for proteins and for the genetic code itself. Nitrogen is created in the later stages of massive star fusion, but also copiously in supernovae. The nitrogen atoms in your DNA were likely created in the violent death throes of a massive star, forged in temperatures of billions of degrees in the moments before or during the supernova explosion. These atoms traveled through space for millions of years, were incorporated into Earth during its formation, cycled through the atmosphere and biosphere countless times, and finally ended up as part of the genetic code that makes you uniquely you. Your very identity is written in stellar matter. About 1.5% of your body is calcium. This element gives strength to your bones and teeth and plays crucial roles in nerve signaling and muscle contraction. Calcium is created in massive stars in the late stages of their lives during oxygen burning at temperatures around 2 billion degrees. When you walk, when you gesture, when you smile, you are moving calcium atoms that were created in the last desperate moments of a star's life, just before it exploded as a supernova. Your skeleton is built from the bones of dead stars. The very structure that holds you upright was forged in stellar death. Your body contains about 4 grams of iron, mostly in your blood, giving it that distinctive red color. Iron is the endpoint of normal stellar fusion, the last element a star can create through fusion before its core collapses. The iron in your blood was created in the heart of a massive star in the final days before its death, forged at temperatures of billions of degrees. Every time your heart beats, it is pumping iron-rich blood through your veins, blood that contains atoms from the core of an ancient star. When you feel your pulse, you are feeling the echo of stellar death, transformed into the engine of life. And the trace elements, tiny amounts of zinc, copper, selenium, iodine, and many others. These heavier elements are exclusively created in supernovae or in even more extreme events like neutron star collisions. They are rare, precious, and absolutely essential. Your thyroid needs iodine. Your enzymes need zinc and copper. These trace elements, though they make up less than 1% of your body, are crucial for your health. They could only have been created in the most violent events in the cosmos. You need the deaths of stars to function. Your body is a treasure chest of rare stellar elements gathered from across the periodic table. Let this sink in. There is not a single part of you that is not made from stars. Your bones, not your blood. Your DNA, not your thoughts. The neurons in your brain that fire when you think, when you feel, when you remember, are made of stellar carbon and nitrogen and oxygen. The synapses that connect them rely on calcium ions from dead stars. Consciousness itself, whatever it is, emerges from the interactions of stellar atoms. You are a way for the universe to know itself, as Carl Sagan said. Where, not metaphorically, literally. You are the universe organized into a pattern that can think and feel and wonder about its own origins. And those origins are written in the very atoms of your being. This revelation extends beyond you as an individual. Every person you have ever known, every person you will ever meet, is also made of stardust. The person you love most in the world is built from the same stellar elements as you. The child in your arms, the stranger passing you on the street, the person on the other side of the world who speaks a different language and lives a completely different life. All of us are made from stars that died before Earth was born. We are family in the most literal and profound sense. We share not just a common ancestor in some ancient organism. We share a common origin in the cause of ancient suns, but it goes further. Every living thing on Earth shares this stellar heritage. The tree outside your window is made of stellar carbon and oxygen, pulling them from the air and soil. The bacteria in your gut, performing chemistry essential for your survival, are using stellar iron and zinc. The whale in the ocean, the bird in the sky, the ant on the ground, all of them are animated by stellar atoms. Life itself is a pattern that stellar matter has learned to take, a way for the universe to organize some of its material into something that can grow, reproduce, and evolve. We are not separate from nature. We are nature. We are all made of the same stuff, and not just life. The Earth itself is star matter. The silicon in sand, the iron in Earth's core, the oxygen in the atmosphere, the water in the oceans, all of it came from stars. The mountains are stellar calcium and silicon. The air you breathe is stellar nitrogen and oxygen. The ocean is stellar hydrogen and oxygen. Earth is not a stage separate from the actors on it. Earth is also stardust. You and your planet are made of the same substance. This world is not just your home. It is your cosmic twin formed from the same nebula made of the same elements. You and Earth are siblings, both children of the stars. The moon, our constant companion, is also made of stellar elements, largely silicon, oxygen, iron, and calcium. It formed from Earth's own material in that giant impact billions of years ago. When you look up at the moon, you are looking at material that is literally related to the matter in your own body. The moon glows with reflected sunlight, light emitted by our local star as it fuses hydrogen into helium. But the moon itself, that beautiful silver disk, is ancient stardust just like you. The celestial objects that have inspired humans for millennia, that we wrote poetry about and dreamed of reaching, are our chemical relatives. The sun, the star that makes life possible on Earth, is also made primarily of hydrogen and helium, just like the early universe. But it contains about 2% heavier elements, the enrichment from previous stellar generations. That 2% is crucial. Without those heavy elements, there would be no rocky planets orbiting the sun. No Earth. No you. The sun is a third-generation star, or perhaps even fourth or fifth. It was born from a nebula already enriched by the deaths of countless earlier stars. Our sun is a child of older stars, and we are children of the sun. The family tree of matter extends back billions of years. What about the other planets? Mars, with its red surface colored by oxidized iron from long-dead stars. Venus, with its thick atmosphere of carbon dioxide, carbon from ancient giants. Jupiter and Saturn, massive gas planets containing mostly hydrogen and helium, but also ices made of oxygen, carbon, and nitrogen from supernovae. Even the distant ice worlds of the outer solar system, Uranus and Neptune, are made of stellar elements. And beyond them, the countless comets and asteroids, each one a little world of organized stardust. Our entire solar system is a chemical orchestra, every world playing a different variation on the same stellar theme. This cosmic kinship extends beyond our solar system. Around other stars in our galaxy, we have discovered thousands of planets. Some are hot gas giants. Some are frozen ice worlds. Some are rocky planets like Earth, and every single one of them is made of elements created in stars. An alien planet orbiting a star 10,000 light years away is made of the same periodic table as you. If life exists elsewhere in the universe, as seems likely given its vastness, that life is also made of stardust. We may be separated by unimaginable distances, but we share a common chemical heritage. All life, wherever it exists, is stellar matter arranged into patterns that can think and feel. What does it mean to know that you are stardust? How should this knowledge change the way you see yourself and the world? For some, it is a humbling realization. You are not separate from the cosmos. You are not special or exceptional. You are made of the same stuff as everything else. Your atoms are recycled. They have been part of countless other structures before you, and they will be part of countless structures after you. In a sense, you are temporary. Brief pattern in the eternal flow of matter and energy through the universe. Just one small eddy in the cosmic river, but for others, it is exactly the opposite. It is empowering to realize you are stardust. You are made of the rarest, most complex materials in the universe. The universe began with only hydrogen and helium, and through billions of years of stellar evolution, it created you. Atoms from dozens of different dead stars came together in just the right proportions, in just the right environment, to create a being capable of thought, feeling, creativity, and love. You are the universe's masterpiece. You are what 13.8 billion years of cosmic evolution produces. You are a way for the cosmos to experience itself. That is not humbling. That is magnificent. Perhaps the truth is both. You are simultaneously insignificant and miraculous, small and vast, temporary and eternal. The atoms in your body are ancient beyond measure. They will exist long after you are gone, recycled into other forms. But the pattern they make right now, the specific arrangement that is you, is unique and precious and will never exist again. You are a temporary sculpture made of permanent materials, a fleeting thought in the mind of the universe. But while you exist, you are the universe, thinking, feeling, wondering. You are consciousness arising from complexity, and that is both humbling and extraordinary. Knowing you are stardust can also change how you think about death. What happens when you die? Your consciousness ends. The pattern that is you dissolves. But the atoms that made you do not disappear. They cannot disappear. Matter and energy are conserved. Your atoms will return to the earth to be recycled once again into new forms. Some might become part of plants. Some might be breathed by other people. Some might end up in the ocean, the soil, the atmosphere. In a real sense, you will become part of the earth, part of the ongoing cycle of matter through the biosphere. You came from stars, and you will return to the planet. Your elements will continue their journey, and if you think even further ahead, to the deep future, your atoms have an even longer journey. In about 5 billion years, the Sun will exhaust its hydrogen fuel and begin to die. It will swell into a red giant, perhaps engulfing Earth entirely. If Earth is not destroyed, it will be scorched clean, all traces of life incinerated. But even this is not the end of the story. The Sun will eventually shed its outer layers, returning much of its material to the interstellar medium. Your atoms, having spent billions of years on Earth, will be liberated once again. They will drift through space, perhaps to be incorporated into a new stellar system, perhaps to be part of new planets, new life. Your atoms are eternal travelers. Understanding stellar nucleosynthesis also gives you a deeper appreciation for the complexity and fragility of existence. The universe could have easily turned out differently. If the strong nuclear force were slightly weaker, atoms heavier than hydrogen could not exist. If it was slightly stronger, all hydrogen would have been converted to helium in the Big Bang, leaving no fuel for stars. The fact that carbon can form at all requires a remarkable coincidence of energy levels in atomic nuclei. The universe seems almost fine-tuned to allow complexity, chemistry, and life. We live in a Goldilocks universe where the conditions are just right. And we are made of just right stardust. Finally, knowing you are stardust connects you to the broader human quest for knowledge. For thousands of years, humans wondered about the stars. We created myths about them, used them for navigation, worshipped them as gods. But we did not know what they were. Only in the last century have we unraveled the mysteries of stellar evolution and nucleosynthesis. Only in the last few decades have we confirmed that we are made of the same elements as the stars. This knowledge is the product of countless scientists across generations, building on each other's work, driven by curiosity and the desire to understand. When you look at the stars and know what they are, you are participating in humanity's greatest achievement. Understanding. So, how do you live with this knowledge? How does knowing you are stardust change your daily life? Perhaps it brings a sense of perspective. The problems that seem overwhelming, the stresses and anxieties of modern existence, they are real and valid. But they are also temporary. You are made of atoms that are billions of years old, and those atoms will continue long after your current concerns are forgotten. This is not to diminish your experiences, but to place them in a larger context. You are part of a story that is unimaginably vast in both space and time. Your individual life is one brief chapter in an epic that spans the cosmos. It might also bring a sense of connection. In a world that often feels fragmented and divided, the knowledge that we are all literally made of the same stuff can be unifying. There are no fundamental differences between humans. No race, nationality, or identity is cosmically special. We are all patterns of stardust, temporarily organized into human form. The person you disagree with, the person you find difficult, the person on the other side of the world, they are your cosmic sibling. Their atoms came from the same stellar forges as yours. This shared heritage does not erase differences or solve conflicts, but it provides a foundation of common ground. A reminder that we are all in this together. Knowing you are stardust might also inspire a sense of responsibility. You are made of rare and precious materials, created at enormous cost in energy and time by the universe. Elements that could only be forged in the most extreme conditions. You are, in a sense, a custodian of these atoms for a brief time. What will you do with them? How will you use this temporary pattern of stellar matter that is you? Will you create? Will you love and dazzle? Will you help others? Will you learn and grow? Your atoms will be recycled, but the impact you make, the ways you change other patterns of stardust, those effects can echo forward into the future. It might bring a renewed sense of wonder. In a world where we often feel we understand everything, where mysteries are solved and magic is explained away, the story of Stardust restores genuine awe. The fact that this is all scientifically true makes it more amazing, not less. You are a walking miracle. A collection of atoms that should not exist, created by processes that seem designed to prevent complexity, brought together by an incomprehensibly unlikely series of events, and somehow organized into something that can think about all of this. Every time you look at your hand, every time you feel your heartbeat, you are in the presence of something extraordinary. You carry the cosmos within you. For some, this knowledge brings a spiritual or philosophical dimension. You do not need to believe in traditional religion to find meaning in being Stardust. There is something deeply spiritual about recognizing your connection to the universe, about understanding that you are not separate from nature but are nature itself, conscious and self-aware. You are the universe experiencing itself, as the saying goes. Your inner life, your thoughts and feelings and experiences, they are what the universe is like from the inside. You are a window through which the cosmos can know itself. That is as close to a miracle as anything we know to be real. And perhaps most importantly, knowing you are Stardust can bring gratitude. Gratitude for the billions of years of cosmic evolution that made you possible. Gratitude for the countless stars that had to die so that you could live. Gratitude for the extraordinary chain of events, each one necessary, that led from the Big Bang to this moment. Gratitude for being alive, for being conscious, for being able to wonder and learn and love. You exist against overwhelming odds. The universe had to do everything exactly right for billions of years to create you, and it did. You are here, and that is something to be grateful for. Living as Stardust means living with awareness. Awareness of your origins, awareness of your connections to all other life and to the planet itself. Awareness of the vast scales of time and space in which you exist. Awareness of the preciousness and impermanence of your pattern. This awareness does not have to be heavy or depressing. It can be liberating. It can free you from petty concerns and remind you of what really matters. It can help you see beauty in ordinary things, knowing that even the simplest objects are made of stellar elements arranged in endlessly fascinating ways. It can help you appreciate every moment, knowing that this particular pattern called you will only exist for a short time, and so we return to where we started. Look at your hand. You are Stardust. You are a collection of atoms forged in the hearts of dying stars billions of years ago. You are organized into the most complex structure we know of in the universe. You are temporarily conscious matter, briefly aware of its own existence. You are the universe looking back at itself. And tonight, as you look up at the stars, you can know with certainty that you are looking at your ancient relatives, your atomic ancestors. The iron in your blood came from stars like those, the calcium in your bones, the oxygen in your breath. You are not separate from the cosmos. You are the cosmos in human form. And that is the most beautiful truth I know. Thank you for joining me on this journey through space and time. I hope you leave this experience with a deeper understanding of your place in the universe and a renewed sense of wonder at the miracle of your existence. You are Stardust. You are ancient and you are precious. You are a temporary pattern in the eternal flow of cosmic matter. And you are the universe, aware of itself for one brief, beautiful moment. If this video brought you peace, perspective, or wonder, please like and subscribe to Cosmic Calm. We create these documentaries to help you find serenity in the infinite. Until next time, look up at the stars and remember who you are. You are home.